Hello everybody, my name is Nicole DeZanti, and I did my research on the Big Bang Theory. Now, what this theory is the leading explanation in cosmology for the universe's early development. It tries to explain the origin of the universe and how it evolved into what it is today. It's a very important theory because it explains, again, the possible origin of the universe we live in. It also provides an explanation for the structure of our universe and the things in it, such as stars and galaxies and things like that. And it also can help us understand why objects in our universe behave the way that they do. So the theory itself actually is a series of stages that we believe the universe took in its early development. It suggests that at some moment all matter in the universe was contained in a single point. We call this the singularity. It was very dense and very hot, and it was about 13.7 billion years ago. So the bang itself was not actually an explosion, as we would think it would be, but it was actually just a very rapid release of the matter and expansion of the universe. And again, this happened about 13.7 billion years ago. So the first moment of this was the very, very quick expansion, and we call this stage inflation. Within 3 minutes of the Big Bang, small particles formed and nuclear fusion took place. However, after about 380,000 years after the Big Bang itself, the universe was significantly cooler from its expansion. It managed to cool down to about 5,000 degrees Fahrenheit, and this led to a period called recombination. This essentially was when electrons were able to combine with nuclei to form neutral atoms, and as a result of this, it caused the universe to become transparent and allowed light to be released. So only after about 380,000 years was light actually released into the universe. However, strangely, after this period was a period called the Dark Ages, in which the universe was very dark and cold. There were very few to little stars in the universe. However, after a few 100 million years, clumps of gas and matter started to form, and they formed the stars and galaxies that we see today. And this was all, of course, due to gravity. Our solar system, the Milky Way, formed about 9 billion years after the Big Bang, which would make it about 4.6 billion years old. Sorry. Okay, so there are a lot of observational evidence that would support the Big Bang Theory itself. And the first one we're going to look at is the abundance of lighter elements in the atmosphere. Now, this evidence, it's all based on predictions made about the current condition of the universe if the Big Bang actually occurred. So one of the predictions was that there would be a certain amount of these lighter elements in the universe as a result of the Big Bang, and it turns out that this is actually very, very close to what we would estimate it would be. So in the very early stage of the universe, roughly a few seconds after the Big Bang, large amounts of elements such as hydrogen and helium were produced. This was called the Big Bang nucleosynthesis. And because of the density and the heat of the early universe, they couldn't support the formation of heavier elements, which is the reason for the abundance of the lighter elements. As you can see from the picture, all of the darker shaded elements are the ones that are most abundant in the universe. And of course, on the table, the lighter ones are the darkest shaded ones, such as hydrogen and helium and things like that. And the next thing we looked at was the cosmic microwave background radiation, or CMB. This is what they call the echo of the early universe. And what it actually is is remnants of the first light emitted that I told you about happened about 380,000 years after the Big Bang. This radiation, it fills the universe and can be seen in every direction. So it was discovered by two scientists named Arno Penzias and Robert Wilson in 1963. They were originally studying microwave signals in the Milky Way, and they discovered a mysterious signal that they were not able to identify. But then they theorized that if the Big Bang Theory was correct, the universe would be filled with the background radiation left over from the creation event, which led to the theory that this CMB was the first light. And that's what they were seeing in the signals. And then I actually have a video to help explain that.
A brand new discovery from these observations is that we have detected the era where the very first stars in the universe ignited. And this era was, for many, surprisingly early. It's only about 200 million years after the Big Bang from the time that you had this intense concentration of all kinds of exotic particles, the time when gas clouds could form and condense and form stars. So we've detected that era for the first time, and it is very early. Well, because it takes the light over 13 billion years to reach us, we are seeing now what the universe looked like then, over 13 billion years ago. So it's a fossil remnant of what the early universe was like. And just like fossils are used to study the past, we use this light to study what the universe was like way back near the very beginning.
What is the map? Well, that picture behind me is really, it's an image of the whole sky, and it's made to image the whole sky on this oval. And you can see in there blue spots and red spots. And what those correspond to are slightly hotter and colder images of the sky. That's a picture there, those hot and cold spots, that pattern is really it's the afterglow of the Big Bang.
We determine, using this cosmic consistency, the age of the universe is 13.7 billion years old. And we've made that determination to 1% accuracy, which is just amazing.
On a sort of deeper, long-term time level, it's this amazing consistency that the picture we can put together of the universe is relatively simple, that the pieces fit together. It's a stunning confirmation of the study of cosmology for many years now. It's just built up, and here it is. In some ways, we're getting to know the cosmos like we know our own backyards. The universe has all of a sudden gotten smaller and much more familiar.
Okay, so now the third piece of evidence of the Big Bang was the expansion of the universe. So in 1929, Edwin Hubble was working at the Mount Wilson Observatory. He was studying our galaxy and distant galaxies as well. And what he did was that he calculated the distances and motions of other galaxies. And to do this, he used something called redshifts, which is similar to the Doppler effect. And the way it works is that he would use the wavelengths of the light emitted from the galaxies, and the redder the wavelength means that they would be farther away, and then the bluer would mean that they would be closer. And what he discovered by doing this is that distant galaxies were actually moving away from us. And another thing he said is that the galaxies that were moving away, if they were farther away to begin with, they were moving away faster. And that became known as Hubble's law. So what happened is that they used this evidence to conclude that the universe is actually expanding. And later this was understood to be a result of dark energy that is accelerating the expansion of the universe. And the way this provided evidence for the Big Bang is that if the universe is expanding at such a fast pace, then it must have been extremely small at some point, which is the singularity that the Big Bang Theory refers to. So I also have a video for this to help explain redshifts and things like that.
In the 1920s, astronomer Edwin Hubble came to work at the Mount Wilson Observatory in Southern California. The observatory offered some of the most advanced technology of the time. Using George Ellery Hale's magnificent telescope, Hubble photographed the nebulae, faint clouds of light that were a mystery to astronomers. When Hubble examined his photographic plates, he discovered a Cepheid, a kind of star that varies in brightness over a period of time. Hubble studied the variation in brightness and used the data collected to calculate the distance to the star. By his calculations, this star and the galaxy it's a part of were much further away than anyone had ever imagined, and the universe was much larger than the Milky Way galaxy.
What he found was that the distance to M31, the Andromeda galaxy, one of, turns out, our nearest neighbors, is about 2 million light years. So people have been talking about the scale of our galaxy, 10,000, 20,000, 30,000, maybe 100,000 light years. What this meant was that M31 and all those other galaxies were not part of our system. They were themselves big systems equal to the Milky Way.
Scientists now know that there are billions of galaxies, and each galaxy has hundreds of billions of stars. Hubble's discovery of the stunning size of the universe and the massive number of star systems within it revolutionized our picture of the cosmos. That discovery alone would have made Hubble one of the great astronomers, but he continued to study distant galaxies and made an even greater discovery. For 5 years, he gathered data on the movements of galaxies, recording their path and direction by studying the wavelengths of light. Different wavelengths of light appear as different colors of light. If a galaxy is moving away, its wavelengths of light are lengthened. This light appears redder. The faster the galaxy is moving away, the redder the light. If a galaxy is moving closer, the light wavelengths are shortened, so the light appears bluer.
After many years, Hubble could sit down and look at this great quantity of information, and he plotted a chart. He plotted for the nebulae the motions against the distances, and he found something truly amazing, a straight line.
He found that the distance of a galaxy is proportional to its velocity. So as you go twice as far out, turns out the velocity is twice as big. You go 3 times as far out, the velocity is 3 times as big. We live in a world, a big world, a universe, where everything's rushing apart, and it's happening in a way we call Hubble's law, where the velocity is proportional to the distance.
Hubble's startling discovery means that the universe is expanding, and that concept forms the basis of the Big Bang Theory, which says that the universe began between 10 and 20 billion years ago from a state of enormous energy, density, and compression, and it has been expanding ever since.
3, 2, 1, and liftoff of the Space Shuttle Discovery with the Hubble Space Telescope, our window on the universe.
On April 25, 1990, the NASA crew aboard the Space Shuttle Discovery deployed the famous telescope named after Edwin Hubble. It orbits about 380 miles above Earth's surface. That high up, the Hubble can view the cosmos unobscured by Earth's atmosphere, 24 hours a day, 365 days a year. Technology has advanced since Edwin Hubble's time, but the work remains the same. The telescope's job is to collect images of stars in distant galaxies. These images help astronomers measure the age and size of our expanding universe.
Okay, and just to quickly explain the graph on the right, it pretty much illustrates Hubble's law and how he came to his conclusion. As you can tell, with greater distance as it goes towards the right, that's more distance, and as it goes up, the velocity goes up. So farther galaxies have higher recessional velocities, which is basically just saying that as the galaxies move farther away, they move faster farther away. Okay, so in conclusion, the Big Bang Theory is very, very, very important to the topic of astronomy. It relates to everything we study in astronomy, the stars, the galaxies, nebulas, planets, things like that. And many think that since it's a theory about the beginning of the universe, it only tells us about the past. However, it's important to take into consideration that understanding how the universe began will affect how we interpret what's happening in the present and what will happen in the future for our universe. So, yeah, so the Big Bang Theory is very important. Thanks for watching.